So now you know how to conduct an independent samples t-test, how to run the stats, how to interpret, how to write up the findings. That is the first of the two-sample tests that we're going to learn. What is the second of the two-sample tests that we're going to learn? It's called a paired samples t-test. It's where we have the same group being measured more than once. So let's learn about this paired sample t-test. There was a reality television show called The Biggest Loser that would bring on contestants who were morbidly obese and then over the course of many weeks take them through a diet and exercise program that led to extreme weight loss. The reason it's no longer on TV is because it turns out this is not really the best way or healthiest way to go about this, and that many times the people who had gone through the program ended up gaining the weight back or having other health problems. But we're going to use that example for this repeated measures test, because what it's going to illustrate is the same group being measured more than once. A paired samples t-test tests whether the average difference between two means is statistically significantly different than 0. What we have is a population of individuals from which we choose a sample. That sample is going to have a mean, and that we're going to call the weight before. This is the starting weight. Then we measure them again at the end of the reality television show or at the end of the intervention, and we have a second weight. It is the weight after, which also has a mean. And we're looking for whether these means are different. However, we're not simply measuring the mean difference. What we're really interested in is the difference score for the individuals. I'm going to come back to difference scores here in a moment. But I need to tell you, how do we get to paired samples? There are two ways to get to paired samples. The first is the one that I've been telling you about, where we have repeated measures. This is the same subjects used in both treatment conditions. Sample 1 are the same people as sample 1B. Each individual is measured twice. This would be like a before and after study. If we're doing a simple example where we have a group of people who are receiving a training, we might test them before the training, and then we test them again after the training, maybe it's an hour later, and we see if they've learned anything before and after. Each individual is measured twice, such as the same group of men being weighed before and after an exercise program. Paired samples t-tests are also known as repeated measures, paired samples, matched samples, or a within subjects design. The second of the two ways that we can get paired samples would be to use twins, or something like twins. In a matched sample, subjects in the experimental group are matched with control subjects who share the same characteristics. So for instance, if we're doing a true twin study, we might be studying exercise. We have the twins, 1 and 2, and we simply group them based on the twin who exercises more versus the twin who exercises less. One's going to go into the more group, one's going to go into the less group. Now, there will be differences between those twins, and there will be differences between them and others, but we're really just using each individual as their own control group. So let's say that we have 2 twins, and one is an Olympic athlete, and the other is just a really, really good college athlete. Both of them are going to excel probably other twins in the study, but they are not being compared to those other twins, they're being compared to each other. That's what makes this a paired samples test. This is often used when we're testing rare variables, or ones where it's very difficult to get someone who's the same, or we don't have the twin. So what we might do if we're studying heart patients is we need somebody else in the hospital who is of similar height and weight and smoking characteristics, so forth. So what we do is we get the archival data from hip replacement patients. We find matching individuals, we match them up with the heart patients, and we can do a comparison study of what happened based on some treatment that was being done. Now, I mentioned that difference score, and I need to go back to that to explain what we're doing. We are not comparing within the group. We are comparing within the pairs. In other words, each individual is serving as their own control group. We will calculate a difference score to measure the amount of change between those measurements. This is going to be computed for each individual, if we have the same group being measured twice, or for each twin, if we're doing our paired sample study. So we have, in our example with the weight, the sample 1 is our before weight, and then sample 1B is the after weight. The reason that we're doing that is that changes can mean something different depending upon your starting point. This is what makes this a dependent measure. If you go on this reality show and you lose 100 pounds, it makes a difference whether you started at 400 pounds and dropped, or you started at 200 pounds. Those are statistically, not even statistically, those are just big differences based upon where you started. Our difference score is looking for the differences within those pairs. The null hypothesis is that the average difference, collect all the different scores, add them up, divide by n, the average difference score in the population will be 0, or h sub 0 colon mu sub d equals 0. That the overall difference will be washed out. Some will increase, some will decrease, but overall it's going to be a wash. For our example, we're going to do clickers versus food reward training, only this time we have paired dogs. Get these pairs of dogs, some will be trained with clickers, some will be trained with food reward. Well, let's figure out our setup. Mickey is a dog trainer studying reinforcement effectiveness. He gets 16 puppies from 8 litters, with 2 puppies from each litter. He matches each puppy in clicker training with its litter mate in food reward training. After training the puppies, he measures the number of correct responses by each puppy in 10 exercises. Was there a statistically significant difference between the 2 training techniques? Now, you may recall that I said pay attention to the blue wording, the blue letters. You will notice that the structure of this research is almost exactly the same, and the blue wording, that's where our differences lie. 2 independent groups versus paired groups. We do this research. Here's what we find. The clicker and the food reward training groups both have a sample size of 8. They are the same. Sample means and sample standard deviations. And if you look at a previous slide, you will notice these are all the same. We are using the same data. The means and standard deviations are the same. And there's an important reason why I'm doing that, because I want to illustrate the power of a paired sample test versus the independent sample test. And I'll show you more about that when we do our interpretation. The research design for a paired sample test. The independent variable compares only 2 repeated measures or matched samples or groups. It's categorical. If we have more than 2 repeated measures, we'll use a repeated measures ANOVA. That initial sample may be randomly selected from the population, but our matched sample, either the twin or sample 1B, is dependent. The second score is dependent upon the first score. They will be correlated. Sample size should be greater than 30, but because we're using pairs, it would be 30 for one group, essentially. So 30 individuals or 30 pairs of twins. The dependent variable is going to be at the scale level. It's quantitative. It has a mean, which is known, but the standard deviation of the population is unknown, and that's why we're going to be using a t-test. We want to be sure to check the assumptions for any test that we're going to do. The first assumption that we're going to check is outliers. We want no extreme outliers in this data set. Outliers can create leverage. They can change the findings. We also want no missing data. If we had a missing data with pairs of twins, we'd probably just have to drop both of them out of the study. We just can't compare two data points that don't exist. And then with dependence, this is the opposite of independence, we're using a paired sample t-test because the assumption of independence has been violated. These dependent variable data are dependent. They are paired or matched. We know that going in. So sometimes when an assumption is violated, it doesn't mean that something has gone horribly wrong. Maybe that's a feature, not a bug. We simply use the test that is appropriate to the type of data that we have. The assumptions that we would test after we have collected data would be normality. Same idea, we're going to look at our dependent variable, make sure it's normally distributed. If so, then the central limit theorem assures us that even with small sample sizes, the assumption will be met. And if the Shapiro-Wilk test is statistically significant, or we have non-normality, if we have more than 30 in our sample size, then the assumption of normality can be assumed to be met close enough. When we did an independent samples t-test, we had to test for the variances between the groups. We used Levene's test for that. We don't have Levene's test for the paired samples t-test, and here's why. There is no variability between the groups because there's only one group. Same group measured twice. Any variability has to be due to the treatment or just random variability within the sample. We don't have two groups, so we don't need to test for variability between those two groups. And as long as our sample size is greater than 30, the t-test is going to be robust. And that brings us to step number 2. We're going to select the null and the alternative hypothesis. The null hypothesis is that the population mean difference is 0. We're going to write that as h sub 0 colon mu sub d, or the average difference, equals 0. Some increase, some decrease. Overall, it's a wash, same as mu1 equals mu2. The average difference is 0. The alternative, h sub 1 colon mu sub d, does not equal 0, or mu1 does not equal mu2. We'll usually write our null and alternative in this way as the mu sub d equal or not equal, and because we have the equal and the not equal, then we are doing a two-tailed test. Step number 3, select a criterion for statistical significance. We're going to keep our alpha level set to 0.05 as we've done for the previous test. Our critical value is going to be based on the alpha level of 0.05 and the degrees of freedom. Remember, degrees of freedom is n minus 1, only in this case, the n is the number of pairs. If we have 8 pairs of twins, then our degrees of freedom will be 7. We can assume that we're using an alpha of 0.05 two-tailed test unless we're told otherwise. Once we have that information, we can calculate the critical value, and we're going to go back to our spreadsheet in Excel in order to do this. Let's go to the tab for critical values, t, and proportion. First of all, we need our degrees of freedom. We have 8 pairs of dogs. Well, n minus 1 is 7. 8 minus 1 is 7. Our degrees of freedom is 7. And so, for the critical value for alpha 0.05 two-tailed test, plug in 7 for our degrees of freedom, and we get a critical value of 2.365. And as I've told you with the previous example, we can change the alpha level, we can change one or two-tailed test for this part of the spreadsheet, and we can dial in that critical value if it's going to be different. Another way of determining the critical value is to go to students' t-distribution table. We are doing a two-tailed test at alpha of 0.05 with 7 degrees of freedom. We find that the critical value is 2.365. So either of those are 2 ways that we could calculate our critical value. And now we're ready for step 4. Let's actually calculate the test statistic. Here is the formula that we could use to do the test by hand, but we're not going to do that. We're going to go back to JASP. So open up a fresh iteration of JASP. Or what you may end up doing if you already have JASP open is to click on the main menu icon, go to Open, Computer, Desktop. And on the desktop, you will find a data set for the paired sample t-test, the one that we downloaded before class began, put it on the desktop. Now we have two variables, clicker and food, and notice that they're both scale level variables. Those are the two pairs. And the structure for the data is going to be different than the structure for the data in the independent samples t-test. We have two columns, both have scale level data. We don't have the groupings. The groupings are the headers. Here's how we're going to do this. Let's go to t-tests, and then under t-test, we're going to get our paired sample t-test, and we need to set up the variable pairs. We'll do that by moving clicker in first, and then pair it with food. We can only put scale level variables in this variable pairs. Now, as we've done before, for the tests, we'll do students t-test, but I want to show you what the non-parametric alternative looks like. That's called the Wilcoxon signed rank test. The alternative hypothesis is mu1 does not equal mu2, or measure 1 does not equal measure 2. These two groups have different means. Under assumptions checks, let's get normality. And then for additional statistics, location parameter, confidence interval of 95%. Let's get our effect size, and we want to be sure to correct for correlation. I'm going to explain that later. But right now, just get the effect size and correct for correlation. Descriptives, and under plots, we're going to get descriptive plots, rain cloud plots, and because this is a paired test, let's get rain cloud difference plots. And I like to use the horizontal display. I think it just looks better that way. As you have been entering these data points and selecting the types of tests and the other settings, you'll notice that the results are appearing in the results window. Let's take a moment to scroll through, and we'll go through in the order that we would if we were doing a real test. We'll start with our assumptions, our descriptive statistics, and then we'll move into interpreting the full-on paired sample t-test. For our assumptions checks, we have a test of normality using Shapiro-Wilk, comparing clicker versus food, and the p-value is 0.037. That is statistically significant at the 0.05 level. So we're going to need to look into this. Why do we have a statistically significant non-normal test? Now we could just gloss over that, maybe interpret it at 0.01 instead of 0.05. But when we look at the plots, we're going to see what's actually going on and what's driving that non-normality. For the descriptive statistics, we have the sample size of 8 for each group, mean and standard deviation for each group. We're going to need those for our APA style write-up. So now let's take a look at our plots. Notice with our plot, our bar plot here, that the mean of the clicker group is not captured by the mean of the food reward group. That means that those two groups are different, which is a little weird because it's the exact same data, exact same mean difference as with the independent samples test, and yet with the paired sample test, they're different versus not. And part of the reason can be seen with this rain cloud plot where we're seeing the individual scores and their pairs. Now you'll notice that the overall pattern is flat line or slight drop, except for there's one right here. That slope is really different than the others. And that is what an outlier looks like in a paired sample test. And what we're going to find is that outlier is probably what's driving the differences that we're finding. The outlier and the leverage, which also contributed to the non-normality finding that we had from our assumptions test, that's what's creating the problem. If I was doing a real research project, I would definitely want to address this outlier. I'd probably just drop it out of the study. However, this is a learning opportunity. So I'm going to leave that outlier in because I want you to see what happens when we have an outlier in our data set and how that can affect our findings. Turning to our interpretation of the paired samples t-test, you'll notice I have both student and Wilcoxon. These are going to look very, very different from each other. Wilcoxon is using a Z sample versus the T test statistic for the students. But pay attention exclusively to students' t-test. The test statistic is 2.758. Our critical value is 2.3. 2.7 exceeds 2.3. It is over the fence. The degrees of freedom is 7. That's the number of pairs. There were 8 pairs. Our p-value is 0.02, which is less than 0.05. And you'll notice that our 95% confidence interval, both the lower and the upper are positive, which means it does not cross our null hypothesis value of 0. So this is a very different finding than we had with our independent samples t-test. Remember, with independent sample, it was non-significant. But this time, with exactly the same data, exactly the same mean difference, we have a statistically significant finding. What explains that? I'm going to unravel that mystery in a moment as well. Now, the other thing I want to point out to you is the effect size. Remember, we use that corrected effect size. So the effect size in this test is a 0.77, or maybe round that up to a 0.78. All of this information can be written up as t with 7 degrees of freedom equals 2.76, probability of 0.03, 95% confidence interval of 0.18 to 2.32, and our effect size of 0.78. This is a statistically significant finding. These groups were in fact different. Now, before we interpret this any further, I want to show you how we would do our paired sample t-test using Excel. So for this example, we're going to go back to our Excel spreadsheet, and we're going to be looking at the example for the paired sample t-test using the ToolPak. On the ToolPak tab, you will find the data that we're going to be analyzing. We'll be using that ToolPak, which we can find in the Data ribbon. So click on Data, and then Data Analysis. This time, we will choose t-test paired to sample for means, and click OK. For variable 1 range, choose B1 to B9. For this type of test, sometimes including the entire column can make it wonky, so we're just going to select the actual data points and the header. For variable 2 range, select C1 to C9. Notice that the scores are paired in rows. Our hypothesized mean difference is 0. Check label, because we have headers. Alpha is set to 0.05. Select our output range, and then click OK. Let's take a look at what the findings look like using Excel. For the paired sample t-test, we see the mean, the variance, the observations. Notice this is variance instead of standard deviation, as we saw with the other examples. Pearson correlation, because these are dependent measures, they are correlated. That's going to be important later on when we talk more about effect size. Hypothesized mean difference is 0. We've set that. 7 degrees of freedom, t-statistic is 2.758. And for a two-tailed test, that exceeds the critical value of 2.3. Our p-value is 0.028, statistically significant findings. Now we have to interpret these findings. I'm going to be relying on the JASP findings. For step 5, interpret the results and write up the findings. There are 3 ways to determine statistical significance. The first, does our test statistic exceed our critical value? And in this case, yes, it does. That t-value is over the fence of our critical value. How about our probability? 0.028, that is less than 0.05, which of course is our cutoff, and the difference of 0, the hypothesized mean difference of 0, is not included in our 95% confidence interval. All of this tells us exactly the same thing. There is a statistically significant difference. We would reject the null hypothesis for this test. But as before, there's something that bugs me about these findings. And that is, when we did exactly the same data points and exactly the same mean difference with an independent samples t-test, it was non-significant, but this time it is significant. What is going on here? Let me show you how to do the APA style write-up, and then I'm going to make everything understandable. I'm going to explain why we're seeing the differences that we do. For our APA style write-up, a paired samples t-test was conducted to determine whether puppies trained with clickers performed better on exercises than dogs trained with traditional food reward training. 2 puppies were selected from 8 litters, and each puppy was paired with its litter mate. The first group was trained using clicker training, and the second group was trained using food rewards only. And again, I'm making sure to include sufficient information that you could replicate my study, do exactly the same thing as I have done. Replication is very important in science. Now let's show them that we know what we're doing. We checked our assumptions. Preliminary data screening showed a deviation from normality in the difference scores. I'm documenting my Shapiro-Wilk. However, the decision was made not to transform the data. In the real world, I think I would have transformed the data or done something about this. But again, this is a learning opportunity, so we'll see what happens when we leave in that outlier that's affecting our normality. The training groups were statistically significantly different. Here's my t-value, my probability value, corrected d, the confidence interval. The mean for the clicker training group was higher than the food reward group, means and standard deviations both included. The corrected Cohen's d effect size was 0.78. That was a large effect size. These findings support the idea that clicker training is more effective than traditional food reward training. Now, I've been teasing this idea that there's something about these data points that bug me. The results are not clean. This is not giving me the type of results that I would expect if I'd done this research project properly. Something is wrong. Really, 2 things. First, we have the same mean difference, but different effect sizes. Second, the independent and paired samples are different findings. Now, this first mystery is not quite as apparent because I used the corrected effect size. If I had used an uncorrected effect size, we would see this difference more obviously. And I am going to dwell on that in just a moment. But the second mystery is, why was one test significant, the other one was not significant, but the mean differences were exactly the same? Well, paired samples tests, the second test that we did, are more powerful. They're more likely to find statistically significant differences in the same data set. Second problem was that independent sample test was underpowered. The sample size was just too small. 8, or 2 groups with a total of 16, is just not enough. This is probably what led to a type 2 error. And the third is that our paired sample t-test had an outlier. And that outlier probably led to a type 1 error. So what we have is errors on both sides. Well, I need to let you know I did that on purpose to illustrate this point. And the takeaway is we always want to check our data and check our assumptions. Because if we don't, we can get errors, type 1 or type 2, finding an effect that doesn't exist or missing an effect that does exist. We can get those kind of errors by not looking closely, by simply blindly doing a test and not really studying our data points. We can make mistakes. There's one last thing that I want to talk to you about, and that is effect size for independent samples versus paired samples. If we use a non-corrected paired samples effect size, we get a different effect size than we do with our independent samples. Now, because I showed you how to use the corrected sample, or rather corrected effect size, we didn't see this, but I'm going to kind of roll back and show you what could have happened if we hadn't used that corrected effect size. This is Jacob Cohen, and he wrote the book, the Bible on power analysis, called Statistical Power Analysis for the Behavioral Sciences. This is where all of these ideas come from. And Jacob Cohen was an incredible statistical mind. He was the one who really promoted the use of effect sizes. In fact, I enjoyed his work so much that a buddy of mine made up a song called Leonard Cohen's D to the tune of Leonard Cohen's Hallelujah. We're using Jacob Cohen's D effect size and explaining that in music. I suppose that Hallelujah is copyrighted. Maybe I should AI a new tune with the lyrics that I have for this song, and maybe I could post that. So I'm going to see what I can do about that. In the meantime, Cohen's D standardizes the mean difference. This is the measure of how big the difference was. When we do statistical significance hypothesis testing, like p less than 0.05, we're using a cutoff score, and we're seeing whether, let's say, our critical value exceeds that fence. Let me draw an analogy of what we're doing. Let's say we go to Silver Dollar City in Branson, Missouri, and we're going during Christmas season, and so they have all of the lights up decorating Silver Dollar City, which is what you see here. Notice that when we try to get onto a ride, there'll be some kind of sign about ride safety, and there will be a sign that says, "Are you tall enough to ride?" There will be some kind of measurement. In this case, it looks like about 51 inches. And what you would do is stand next to this sign and see whether you exceeded that cutoff score. Now, you being college students, you'll probably have no difficulty exceeding that cutoff score. But do you remember when you were a kid? Did you ever not get to ride on a ride because you were not above that line? You weren't tall enough? Or even worse, your big brother got to ride on the ride, but you didn't because he was tall enough. He was over the line, and you were just under the line. I remember standing on my tiptoes, trying to just get above the line. This was a big deal when you're a kid, when you're really close to that line, that cutoff score. But here is what we're learning from that cutoff score. The standard for are you tall enough to ride is the same as a p less than 0.05 critical value. Being taller than the line doesn't tell us if you're tall or how tall are you. It only tells us if you are tall enough to exceed this criteria. You are over the threshold criterion. If you've ever spent any time at Silver Dollar City, there's a fella down there, I think they call him Shorty, and he's every bit of 7 feet tall. He's a tall guy. And this guy would exceed the critical values for all of these rides. But people never say, wow, are you tall enough to ride the rides? They want to know, how tall are you? Really tall, thin fella. And he'll stand out if you ever see him there at Silver Dollar City. In order to know how tall he is, we need a yardstick, a measuring tape, something that we can actually measure the difference of his height from the ground. That's what we really want to know. That is analogous to an effect size. P-values, cutoff scores, tell you, are you tall enough? Is this difference big enough to be unlikely to be due to chance? But it doesn't tell us how big the effect really is. That is why we need an effect size. Tell me how big the effect really is. Cohen's D is our measure of effect size in t-tests. This is the formula for Cohen's D for independent samples t-test. Only works for independent samples, doesn't work for paired samples. 2t over the square root of n. Plug in the values from our test that we've just run. We get a Cohen's D effect size of 0.79. Keep that in mind. This is the formula for a paired samples t-test. Only works for paired samples, does not work for independent samples. It's t over the square root of n. Plug in the values from our paired samples test and we get a Cohen's d of 0.98, which is really different than that 0.78 or 0.79 that we got from our independent samples t-test. So what the heck is going on here? Let's look at these findings. For the independent samples t-test, our Cohen's d is 0.79, but for the paired sample t-test, Cohen's d is 0.97. That's a dramatic difference in effect size, especially when you consider that the mean difference of 1.25 is exactly the same for both of these tests. What is happening here? The answer is correlation, relatedness. The after score is dependent upon the before score. We have paired or dependent measures. The correlation between those sets of scores is affecting our effect size. We need to correct for the correlation between the before and after scores in order to get an accurate, legitimate effect size. The formula for correcting comes from Dunlap et al., 1996, and it is this. Plug in the numbers from our paired samples test, and we get a Cohen's d effect size corrected to a 0.78, which is pretty much the same as the 0.79 that we got with our independent samples t-test. This is the correction that makes it all work. There are a few other videos that I would encourage you to look at. One would be how to interpret a negative t-test. If you haven't seen this one already, the takeaway is if your t-test is negative or your effect size is negative, the magnitude is the same as if it was positive. Typically what I do is just drop the negative sign. A second video is called Cohen's d effect size for t-test. It's where I go into an explanation of what I've just told you about repeated measures and why we need to use that correction. And the third video is called Setting Up T-Tests. This one is really worth a view because on the test there will be an example where you want to do, let's say, an independent samples t-test, but your data are structured for a paired samples t-test, and you need to restructure your data so it works for that independent samples test. And what you will be doing then is creating one column, which is all scale level data, and a second column, which is categorical. The category name will match up with the first set of scores, and the second category name with that second set of scores. But 2 columns total, one is scale, one is categorical. All right. That is all that we have for this week. I want to thank you for being here, and I'll see you guys next time.